Okay, so because of some technical issue, we will move Professor Zhao Yang's presentation first. So he will be giving it in an old-fashioned way of speaking directly to the audience and not to the camera. Professor Zhao Yang is a colleague of mine from the School of Material Science and Engineering, and he will be giving a talk slightly different from the rest of the guys who are more coming from an experimental point of view. Professor Zhao will be coming from the theoretical point of view. Let us welcome Professor Zhao.
First of all, I'm very humbled to be among the speakers panel of this symposium in honor of Professor James Barber. Before I get to my topic, I just like make a few comments. So many have commented on the great career of Professor Jim Barber, and I just like to add, as a younger investigator, I just like to add my 2 cents. Okay, I became familiar or was introduced to Professor James Barber about 10 years ago, maybe 8 or 9 years ago, during the time that we were applying for a CRP grant and on photosynthesis. Our topic was towards efficient sunlight harvesting. And Professor James Barber was such a wonderful person, helped us such a great deal. And we not only got our $10 million grant, and we brought that grant to a very successful close 5 years later. And I have never seen a senior, extremely achieved individual like James Barber, who took such great pleasure helping us younger investigators. And I have no way of paying him back. Actually, the only way I managed to find to pay him back is buying him beers over some tree crack. And even that is denied on this trip. He just told me he had a lobster yesterday. Anyway, okay. So I will be I'm sure many in my school, for example, the School of MSc, feel the same way that I do, okay, including Joking, Lydia, etc. So, all right, I'm going to talk about from theoretical perspective the chlorophyll from light harvesting complex 2, the exton created, and how the electronic energy is relaxed and dissipated, and eventually goes to the QY excitation, etc. Okay, and the LHC2 compound is the most abundant light harvesting complex in nature, and here this is the CHLA molecule, and this is the beginning of photosynthesis, and plays an essential role in the conversion of sunlight into chemical energy. And it's very important. We study the inter-pigment relaxation as well as inter-pigment electronic energy transfer. And if you look closer, there are many pigments within this compound. Okay, and here, because computational study, including both the nuclear degree of freedom and the electron degree of freedom, is a many-body, very difficult dynamic problem. Okay, we cannot do the entire complex. So far, most of the research has been done only on a single pigment. And here, we will choose a dimer. Okay, this dimer is CLA613, CLA614. And it locates somewhere on the boundary of this LHC2. And why do we choose this dimer? Okay, number one, the dimer with a very short inter-monomer distance, and it's relatively isolated from other pigments in the compound. Okay, and also because it sits on the boundary, it's sort of an interface between two subunits of LHC2. LHC2 is a trimer, okay? And here I'm only displaying this one monomer here. So that's why they're proposed to be functioning as a energy quencher, okay? That's why this dimer is chosen, because it's quite interesting. And First of all, we will study using non-adiabatic excited states molecular dynamics, the absorption spectrum. Okay, so we basically shine the laser beam onto this compound. Okay, of course, this is in the simulation, and the ground state will be excited to the excited states, and then these excited states will go through this cascade of excited states all the way down to S1. S1 is the QY excitation. And here you will see these different bands. Okay, this is the QY band, this is the QX band, and this group is the B band. And our computational approach is quite flexible as well as accurate, so we can capture the entire process. Okay. Again, our approach is called non-adiabatic excited states molecular dynamics. Since many here are experimentalists, so I will just be brief on the theory part. Just go quickly through it. We employ a mixed quantum classical system. Okay, because of the extreme complexity in the nuclear degree of freedom, so we cannot do quantum mechanics for both degrees of freedom. We can only do quantum mechanics for the electronic degree of freedom while leaving the nuclear degree of freedom to a classical simulation. But that classical simulation is not the simple, simplistic classical simulation. This one is actually with an algorithm called Fourier switch surface hopping. Okay, it allows the system to hop from one energy surface to the other when the criterion is satisfied. And on top of that, we will just use a constant temperature Langevin equation. Okay, so the hopping part actually try to mimic the quantum mechanics for nuclear degree of freedom. It's not very quantum mechanical, but it's good enough for the purpose. Okay, and the electronic degree of freedom will use the Schrödinger equation, and these two parts you have a feedback back and forth to make sure that the approach is self-consistent. And initially, we will have excited states coefficient assigned and the nuclear coordinates for all the atoms in the system, as well as the initial velocity. And then we will do constant temperature Langevin dynamics for the nuclear degree of freedom. And then electronically, we will propagate the wave function using the Schrödinger equations. And like I said earlier, that at some conjunction, we will see whether we need to switch energy surface using the surface hopping algorithm. Okay. Once this happens, we have to do velocity rescaling to make sure the energy is conserved during the hopping. And this process can go on and on, okay, until that we have desired, we have reached the desired time of simulation that we wanted. Okay. Then we will proceed using statistical average over all the trajectories, usually in our simulation, 500 to 1,000 trajectories. Then we try to calculate various physical observables. The Hamiltonian we use in our calculation of absorption spectrum is the semi-empirical level. Okay, it's called the AM1 semi-empirical Hamiltonian, and the simulation is carried out at room temperature for obvious reason. Okay, and these are the QY absorption peaks, QX absorption peaks, as well as the solid B bands that we calculate. In fact, because we're dealing with a dimer, okay, so all these bands, they have actually two states in there. This one is the S1, the S2 band, this is the S3 and the S4 band, and over there, we will have S5 all the way to S10 band. And actually, our calculation also do all the way to S11 to S20, okay. These are just by shown by those higher energy peaks over there. So our laser pulse initially is designed to be a Gaussian peak allocated somewhere around here. Okay, that's where the laser pulse is. And after that, we will just select a configuration. Okay, and then we do our molecular dynamic simulation in connection with this non-adiabatic electronic degree freedom propagation. These are some of our results here. And we compare a dimer relaxation with a monomer relaxation. And we found that the relaxation from the B band to the QX band is slightly slower in the dimer comparing to the monomer. However, the relaxation from the QX band to the QY band is so much faster in the dimer, and therefore the entire process going from the B band all the way to the QY band happens much faster in the dimer comparing to the monomer. Okay, so this you can actually tell from the fitting the data that we get. We basically use this 3-band fitting procedure to fit our computational result. And you can see, for example, okay, the monomer case, B to QY takes 227 femtosecond, while for the dimer, it's only 140. Okay, so and you can see the first step, B to QX, is almost the same, with the monomer slightly faster. However, the dimer is much faster for the step from QX to QY. And we can also actually look at the transitions all the way from S6 all the way to S1. And as you can see, actually various excited states, if we calculate the transition density for that system, we will realize they have slightly different symmetries, as you can see. Okay, this one symmetry, well, the charge density is mostly located on the right-hand side. This one is mostly located on the left-hand side. Right-hand side, left-hand side, right-hand side, left-hand side. So as this system goes from S6 all the way down to X1, actually this involves exton transfer between the two monomers in the system. Okay, so it's going back and forth, back and forth, back and forth. Eventually it goes down to the QY extension. And we have calculated how many times exton has to go back and forth before it reaches the lowest QY band. Sometimes we come up with a number like 20 or 30 times. Okay, so therefore the inter-pigment transfer is quite important for the system. And you can see, well, the procedure is mostly from S6 to S5, S5 to S4, S4 to S3, so on and so forth. But there is also some slight probability as you go from, for example, S5 to S3. So you can go from here directly to here. And that step actually does not involve a lot of inter-pigment transfer. You can see the charge density are mostly on the one side. Okay, slight transfer, a very small percentage. All right. After the calculation is done, we calculate the transition density. Okay, transition density is calculated by using this formula. Okay, this is the ground state wave function. This is the excited state wave function that we keep track of. And this basically shows, especially okay, when m is equal to n. So basically, this is a diagonal element of this TD matrix. The diagonal element basically is showing you, comparing to the excited states and the ground states, how the electronic density transfer, okay, moves around. Okay, so by calculating this transition density, we can learn a lot about how the electronic charge moves around in the system as the system goes from higher excited states to the lowest QY station. Okay. And here I just show some of the results here. Okay, for example, okay, over here on one monomer, okay, this is CLA613. See, this one has a slightly higher charge density, higher than 0.5. Okay, so on average, it's like 0.6, 0.7. Okay. And when the electronic charge is mostly located on one monomer as compared to the other, okay, and we call that higher density monomer called higher monomer. Okay, so we sometimes use this HM to represent it. Okay, so the energy, the electronic density can go from one monomer to the other. If we initially allow the electron to be sit mostly on one monomer, eventually it will have a smooth distribution. Okay, that is, it's almost equally shared by the two pigments. And we can also calculate the fraction of transition density localized on the group X. Okay, and those labels are the electronic orbitals. And these label X can be just monomer 1 and monomer 2. Okay, so if all the orbitals are within the same monomer, then we have just the A group. Okay, A group index is the index of an atom localized in the X group. Okay, when you have this thing, the B is located at the interface of group X and another group, and then we take a 50%. Basically, this TD is shared by group X and the other group. So by this, we can actually do a lot of things. Okay, we can also calculate a participation number. Okay, participation number is calculated by this formula. Okay, when the participation number is 1, the transition density is almost completely localized on the single monomer. If P is 2, and the TD is delocalized over 2 monomers. Okay, so you can see initially it may be more on one monomer. Eventually, it will go down to 1. Okay, so it's a sort of more equally shared by the 2 monomers. Okay, finally, before I packing up this short talk, we're looking into the transient electronic transition density redistribution within the monomer. Okay, so intramonomer excitation redistribution, and we will look at this magnesium atom. Okay, these are the 4 nitrogen atom, and this outer layer we call the inner macrocycle, and finally this is the outer macrocycle. So during the relaxation for a single, time running out. Okay. All right. So I'm sorry. So for this relaxation, basically the system goes like this. Okay. In the B band, the electron density mostly is in magnesium as well as nitrogen atoms, as well as the outer macrocycle. Okay. And towards the lowest, the QY band, it will be on the inner macrocycle. Okay, that is the same if you just simulate for a monomer, or if you simulate a dimer. Okay, and you have 2 monomers in there, and if you look inside one monomer, it's pretty much the same thing. Okay, so I will skip maybe the conclusion. And I would like to thank my PhD student, Furu, who did most of the work, Shania, who already graduated, did some of the ground state calculation, my collaborator from Argentina, Sebastian Alberti, as well as Sergei Tretiak from Los Alamos Lab, who gave us much of the guidance on surface topics.